Okay, welcome Bradley and Jordan, Cesar, Jesus. Today, welcome Ralph. Today is we're continuing on as always, and that's kind of how we go. We don't even do one section at a time. We do two or 1.5. So we're going to finish off 4.10 and then we're going to move to 4.11. So let's talk about the plan of the day, and let me share my desktop. Okay, so the plan, as always, is we'll start with Q&A. If there's any questions on homework or whatever. And then after we do Q&A, we're, as I mentioned, can continue on with 4.10. 4.10 is like that super section, kind of the most important section in the whole book, because it goes on and on and on with all kinds of important stuff. So today we're finishing. And what we're going to do is we'll start out, this will be real quick and simple. It's called the Kronecker delta, and it's just a symbol to do things that you want to do pretty often, and otherwise it just takes too much writing. So it's one symbol to do a lot of writing. Then we'll get into orthogonal matrices and orthonormal bases. So last time we defined what it meant for vectors to be orthogonal, what it meant for vectors to be orthonormal, and what it meant for a matrix to be orthogonal. And this time we'll say, well, if you have an orthogonal matrix, then you have an orthonormal basis. And we'll see what that means. So then after that, we'll get into properties of orthogonal matrices. There's a lot of very nice properties. They're like, orthogonal matrices are really wonderful to be able to deal with, as long as you have one. Then after that, we're going to get into the Gram-Schmidt process. I know that probably means nothing to all of you, but it's a nice process of starting out with a basis that is not necessarily orthonormal or even orthogonal, and make it so. So say, what is it? If you have you want to have the same space, you want to find a basis for the space, but you want it to be an orthonormal basis. And we start out with one that isn't, and how do you make one that is? And there were two people, and I bet you can guess who those two people, at least their last names were, that came up with the way to do it. And if you can't, then you're asleep.
Newton.
Is it?
Huh? No, not Newton.
Is it Graham and Schmidt?
Yeah, Graham and Schmidt. Yeah, that's supposed to be obvious, right? So it's called the Graham-Schmidt process. And we'll talk about how to do that. Then we'll talk about orthogonal projections. They turn out to be a lot more important than you would imagine. And that is if, let's say you have, just geometrically, let's say you have a vector and it's out in R3, and you want to find out what's the vector in a plane, a given plane, that's closest to that vector. Okay, and that'll be the orthogonal projection. So that's kind of how that works. Kind of another word for it is shadow in perpendicular to the plane is another way of looking at it. Okay, but it doesn't have to be a plane. It could be 75-dimensional space. So all of a sudden, it doesn't help at all to visualize. So we're going to have a way to figure this out, formula for it. And then we'll talk about the orthogonal complement. So if we have a vector space, a subspace, and what we want to do is want to say, well, what about things that are orthogonal to it? And that turns out to be a subspace also. And that's called the orthogonal complement. And I'll rigorously define it. And we'll talk about the closest point to a plane. Okay. So again, a little geometry today, but you can expand on that and leave the three-dimensional world and move into whatever dimension you want and do the same thing. And then comes, in my opinion, the most important application, probably in the course actually, and that is least squares. So you've heard of it, some of you have done it. Anyone who's taken stats knows it, at least for the least squares line. But it turns out that you can do least squares anything. And you can come up with the best fitting logarithmic function or the best fitting third degree polynomial or the best fitting line to a set of data, which is nowadays is really important. Having data and try to understand it is just exploding in terms of importance in the last 10 years, probably. It's everything. And it's not just because I also teach stats. It really is a big deal. So you want to be able to handle it. So that is the plan of the day. And I want to remind you, Wednesday, there will be no Zoom lecture. How come?
We'll be taking an exam.
Yeah, you'll be taking an exam. So just let you know, get ready for it. Re-looking at your homework problems is a good idea. There's a practice test. I think there might be one problem in the practice test that goes beyond what we're doing. Because I think I cut it differently last time around. But you have lots of practice problems. I mean, the book definitely has enough problems to work on, that's for sure. And there are a lot of proofs on the exam, just a warning. So that's just a note. And that is the plan for upcoming. So are there any questions that might have happened on homework that was due? Here we go. 4.10 number 69 part C. Okay. Not sure which signs every number except for on top of it. Okay, let's go and copy it. Okay, 4.10 number 69, and I'll just do it and then we'll see what goes on. 4.10 number 69, let me make a snapshot of it. And it's find the kernel. And we wanted part C, so I'll just snip part C down. So again, the instructions are find the kernel. So I'm not copying the instructions. I could type it out, I guess. Okay, so here's our matrix. And let me type it out. Find kernel of A. Okay, so so the important thing is you understand what the kernel is. So the kernel means that it's a set of all x, vector x, such that ax is equal to 0. Any questions on that? Okay. And it's a step-by-step process. It's actually not that hard if you understand the steps. And there was a big theorem we had, and that said that the kernel of A is equal to the kernel of RREF of A. Do you remember that theorem, Cesar? Yeah. So the first step, and again, for this kind of thing, you should know how to do it by hand, but you shouldn't do everything by hand because it'll take you all day long to do any of these problems. But on the test, you might have to do one RREF, and then the rest you can all use a computer. But let's do RREF of A. And did you get that? Was that one of the difficult parts? Okay, so just a minute. Let me make a matrix. It'll be a 3x3. Okay, 1, 0, 1/2, 1. Wait a minute. We just have a 3x3. There should only be 3 numbers in the first row. I'm a little confused about your kernel. So the kernel should just have, it should be a 3x3. So maybe that's a problem right there. Because if you RREF a 3x3 matrix, you get a 3x3 matrix. And so you're not sure? I think you got a different one. Let me double check, but this is the matrix you started with, right? 2, 4, 0, 3, 6, -2, 1, 2, -2. I could double check that was the question you wanted. Yours is 4x4, so let me look at it. You wanted number 69, part C. Maybe I copied the wrong one, but let me check. So 69, part C is 3 by 3. Did you mean part D? Part D is a 4 by 4. Ah, part D. Okay, that changes everything. Or at least it changes the matrix. Yeah, because I wasn't going crazy there. All right, so let me snip part D. Okay, that's better. Okay, so part D is different than part C, definitely. Let me make it the right size. Okay, so now I'll trust you in what you got, which was 1, 0, half 1. And then 0, 1, negative 2, negative 3. And what was the third row? Bottom 2 rows of zeros. Okay, so there's our RAF. And again, computers are good for this. So now what we need to do is we need to read this and figure out what the kernel is. Does that make sense so far? And when we say what is the kernel, what we really mean is what is the basis for the kernel. That's what we want. So the kernel of A is the span. And just to make life easier, I'm going to write it as row vectors, even though they're really column vectors. It's just easier to write in. It's the span of the set. And now we got to come up with it. First thing is, how many free variables are there?
2.
There's 2 free variables. If there's 2 free variables, that means that the dimension of the kernel is going to be 2. So we're going to get 2 vectors out of this. And the way you do it is you let the first free variable be 1 and the second free variable be 0. And when we do that, we get the vector. So negative half comma, and then the second one will be 2 comma 1 comma 0. And then for the next one, now we're going to let the second free variable be 1 and the first free variable be 0. Okay, and that's going to give us negative 1, yep, comma 3 comma 0 comma 1. And that will span, that will be what the kernel of A is. Any questions on this idea? Okay, are there other ways of doing it? Probably, but this is the easiest. Because RREF with a computer is very easy. And then hopefully, and again, if you need me to explain how I got these 2 vectors, if you don't remember how to do that, I can do that. But it's not hard if you know what to do.
Could you do that?
Okay, so what I did in my head is I realized I wrote it in parametric form. So I said, let's call it W, X, Y, and Z. Sound good? So I said W plus 1/2 Y plus Z equals 0. And then I said X minus 2 minus 3. Oh, sorry, minus 2y. Sorry, minus 2, wait, W, X, Y, Y, minus 3z equals 0. And it helps to write y equals y and z equals z. You can always write those, right? Any questions on that so far? Okay, then what I did, kind of more, if you want the formal thing, I looked at it parametrically. Let say u and v be y and z, and you get w is equal to negative a half u minus z. And x is equal to negative 2u plus 3z. Sorry, just positive 2u. And then y is going to be equal to u. And z is v. Any questions on how I got that? Okay, so that's a parametric form of the kernel. So then what I want to do to get a basis, I can let u equal 1 and v, sorry, this should be, the z should be a v, and the z should also be a v. So I let u equal 1, v equals 0. And when I do that, I get negative a half, 2, 1, 0. And that's the first one. Then I let u equals 0, v equals 1, and I get negative 1, 3, 0, 1. Does that make total sense?
Yes.
Yeah. And it's a lot of writing, but there's nothing to it. And that's why once you get good at it, you just do it. Yeah, I could look at the textbook way. Do you think the textbook way is easier or harder? My
guess is it's going to be harder.
Yeah, honestly, I didn't look at it because I know this way and I know it works real well for me. Is that I just RREF. If you found a typo in it, do me a favor, send me an email, and then I can. The good news is I can actually fix the typo in the LibreText version of the textbook. I can't fix it in the Linux version, but I can fix it in LibreText. But the answers aren't in there, I don't think. Actually, I may not be able to fix for the questions, but I can fix an example if there's a typo in an example. That I can do. I have permission for that. Any other questions? And kernel is important, by the way. We'll be coming back to it a lot. Any other questions about anything else? Or did you find this one not too bad, this homework?
I have a quick question. Is there a way to find the magnitude of a matrix?
Well, is there a definition of a magnitude of a matrix?
I don't know.
So there's a few definitions. One is the absolute value of the determinant.
Okay.
But usually we don't even say the word magnitude.
Okay.
Right? Because a matrix isn't a vector.
Yes.
Okay. There is such a thing as a vector way of looking at matrices, and then you can talk about magnitudes of that as a vector after understanding the definition of magnitude and the definition of vector, which you don't know yet.
Sounds
so
good.
Sorry if I just said things that you don't know yet. But
no, that's all right.
Yeah.
Yes, I believe you.
So I've talked a lot that we're gonna make vectors more abstract. So they're gonna be more than just a bunch of numbers with commas in between. So matrices are vectors, and then you can find the magnitude of the vector as long as you have a basis for the vector space of matrices. So I'll just stop there. How's that? So the answer is yes, but it's over your heads right now. Other questions? Okay, if there's no questions, we'll go on to the new stuff. And we have some definitions. So the first one really is just a symbol, but it's a really convenient symbol. I'm not sure if you've seen this before. Anyone seen this before? The delta ij. Anyone seen that symbol? Not seeing you all
No.
jumping. No? Okay. It's a really useful symbol because it comes up a lot and it's a real pain to write down its definition, but it's really easy to write down delta ij. So delta ij is a function of I and j such that if I is not equal to j, it's 0. And if I equals j, it's 1. And that's delta ij. And the formal name for it is Kronecker delta. As you might be able to guess, any guess on who's the one that came up with this idea of making this symbol?
Some guy named Kronecker.
Yeah, some guy named Kronecker. And I actually know nothing about Kronecker. I don't know anything else he's done other than that. But he might have done something. He's been around a while, so way before I was born. So it's a nice thing to have because otherwise it takes a lot of work just to say it. And the symbols are a lot harder to type. You can do it in words, and that takes some time. So this is a really nice definition. So for example, let me give you another way of writing the definition of orthogonal or orthonormal. So V1, just a second, let's do it this way. So V1, comma, V2, comma, dot, 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 comma, VK is orthonormal. And let's say an orthonormal set. If, well, how can we define it in a much nicer, prettier way now?
Delta ij.
Yeah, but we need something before that. What about delta ij? So you got to remember what the definition of orthonormal was. Remember, if vi dotted with vj is equal to delta ij. Where's my delta? Let's try there. Here we go, Greek letters. There's my delta, ij. And that's the definition of orthonormal. Isn't that an easy way of writing it? So very nice to have that. Okay, and you could even say same thing. I is the identity matrix. If, well, we do it again. Aij equals delta ij. Isn't that what the identity matrix is? So this Kronecker delta it's just a very nice symbol to be able to say something that comes up all the time in this class. And that is 0 if you're the same, 1 if you're different. Any questions on this Kronecker delta symbol? Again, it's just a symbol. There's nothing really much to understand, but it's a very convenient symbol. And just when you least expect it, that's when I'm going to use it.
I have a quick question for you.
Sure.
To see if to check to see if a matrix is orthonormal, can you just take the determinant? And if it's not 1, it's not orthonormal?
Okay, so that's a good question. So first thing is, you're saying, does the determinant have to be 1? First thing, it doesn't have to be 1. Just to get you.
Okay.
We're gonna have a theorem about that in a bit. And when you say orthonormal, you mean orthogonal. We never use the word orthonormal for matrices.
Yes.
Like I said, it's don't blame me, don't get mad at me, but I hate this word. But we use orthogonal to mean all the vectors are orthonormal. I think don't you agree that's kind of dumb? But I got to do what everyone, it's not just this book, everyone uses it. Okay, so that's the first thing, is that you could have an orthogonal, or you could have an orthogonal matrix. Let me give you an example where the determinant is not 1. So very easy to come up with one. Hardest part is typing it, but I can make it happen. Okay, what's the determinant of this matrix?
-1.
It's -1. And if you take the dot product of 2 columns, do you get 0?
Yes.
And are the magnitudes of each of the column vectors 1?
Yes.
Then this is an orthogonal matrix, but the determinant's not 1.
Okay.
Okay, so the answer is no.
All right.
Yeah, that you can't do. But it's actually not that hard to decide, to find out if something is orthonormal. I mean, sorry, orthogonal, because remember that it's orthogonal if and only if A times A transpose is the identity. Do you remember that?
Yes.
And it's not that hard to take a transpose. Do you agree? It's easy.
Yeah.
And multiplication is not that hard either. It's not like inverse.
Yeah.
So it's pretty easy to check for orthogonality. But what you can't do is just take the determinant. If you get 1, then if you don't get 1, then it must not be orthogonal. It doesn't work. Okay. But here's what you can say, because it's a theorem that's next. And that is, if we have a matrix such that a matrix has its rows orthonormal, if and only if the matrix itself is orthogonal. Okay. Why does that not immediately come from the definition? How is the definition of a orthonormal, of a orthogonal matrix different than than just the rows being orthonormal? The hint is one word difference.
I'm thinking transpose.
Yeah, because the definition of orthogonal is the columns must be orthonormal, right? And this says that rows are good enough. Okay, so that's what this theorem is saying, is that even though, so it says that if the rows of a matrix are orthonormal, then the columns of the matrix are also orthonormal. Does that make sense? How do you prove this? It's not that hard.
I'm thinking do the definition of orthogonal twice.
Kind of, well, not quite twice, but start with the definition of orthogonal. Okay, and that was A times A transpose is the identity, remember? And also A transpose A is the identity. All right, so let's write that down. Now put it in. A times A transpose equal the identity. And A transpose A equals the identity. Okay. So let's say we start out with an orthogonal matrix, right? Well, what can we do to both sides of these equations? And this was your idea. We could take the transpose. Because that's true. If two matrices are the same, then the transposes are the same. And similarly, we could take the transpose. Okay. Or another thing we can do, well, this will work. Let's try one more time. Let's try this. Okay, and the idea is what we've just done is we've said, well, if AA transpose the identity, then the transpose, then switching the idea of rows and columns also works. Any questions on that? So therefore, since originally the columns were orthonormal, taking the transpose switches the columns from rows. Any questions on that? So therefore, that's true. We're done. And that's the good news, is that taking the transpose, it works. Any questions on that? Okay. So that says that if you want to check to see if a matrix is orthonormal, you can either look at the rows or you could look at the columns. And as long as you get an orthogonal set, however you look at it, then it's orthonormal. Any questions on that idea? Okay, now comes something that you were just talking about, Bradley, I think, and that is a big theorem. And you thought that you had to have a determinant 1, but you don't. But that doesn't mean that you could have any determinant. What we have is that if U is an orthogonal matrix, then the determinant of U is either 1 or -1. You can't have a determinant of 2, for example. What's the easy way of proving this?
A times A transpose being the same as A squared. Then you take the determinant of that and
Okay, A times A transpose is not A squared. In
if
fact, A squared may not even exist. But it's the identity. That's the important thing. Does that make sense? So we know from definition that A times A transpose is the identity. It's not A squared. It's the identity. Does that make sense? A might be a 2x3 matrix. You can't do A squared.
Okay, so then take the determinant to both sides.
That we can do. And that we're always allowed to do. You know, the old math thing, you can always do both sides of whatever you want. And what is the determinant of the identity? That you're all supposed to know? Yeah, that's 1. Okay, but what we can now say is the determinant of A times A transpose, which is 1, because we found that out, is equal to the determinant of A times the determinant of A transpose. That was a theorem we had about determinants. But the determinant of A transpose is just the determinant of A. We had that as a theorem. Do you remember that theorem?
Yes.
All right. Well, guess what? If you have something times itself and you get 1, what do you know about the number?
It's
It's
negative
squared.
1.
It's either 1 or -1, and that's the theorem. We're done. Any questions on that idea? So I like these easy to prove theorems. Any questions? Okay, so orthogonal matrices are nice. Okay, and notice, by the way, if and this is kind of the most important probably, is that if you have an orthogonal matrix and it's square, then A is its own, then A transpose is A inverse. And that's really important. So that isn't here, but I want to remind you. So if A is orthogonal, then A transpose equals A inverse. Let's make that pretty. Why is that really nice to know if you have an orthogonal matrix that A transpose, A inverse is A transpose, or either way?
Because you know that A times A inverse is the identity.
Yeah, that's the proof. But why is it real convenient, this little statement here? Okay, and I should say A is orthogonal and square. You need that too. If it's not square, obviously you can't take an inverse. Okay, it's really nice because transpose is really easy to take and inverse is really hard to do. Okay, so that's the main reason. In fact, if you had a 100 by 100 matrix and you want to take an inverse and you have a computer, how long do you think it'll take? Any guess? Some general 100 by 100 matrix.
A few seconds.
No, it'll crash the computer.
No.
Because it turns out that the number of operations needed to do the inverse is of the order of n factorial, and 100 factorial is too big for a computer. But transpose is very easy because that's of the order of n squared, and n squared is much easier. That's 10,000. Computer can do 10,000 steps in a millisecond, right? But 100 factorial is brutal. I don't know if you can imagine, but that's the big reason why orthogonal matrices are so nice. One of the big reasons. There's another reason we'll get into later, and that has to do with the diagonalization process. But that's another day. Any questions on this theorem and this little extra theorem here? Okay, so next guy is if A and B are orthogonal matrices, then A times B and A inverse are also orthogonal. Okay, that is if A inverse exists and if AB exists. Okay, if they don't exist, you can't even talk about them. How do you prove something like this? Maybe I'll do the first one because it's easy, so is the next one. Any guess? You just go to the definition. You say, well, what is AB times AB transpose? And what are we hoping it is?
I.
Yep. So now we have to go and do it, and we have to use some properties. So that's going to be equal to AB. And AB transpose is B transpose A transpose. That was a formula we had. Nothing to do with orthogonal. That's just always true. But the associative property of multiplication works for matrices. So I can move my parentheses around. And I can write this as A times BB transpose times A transpose. Any questions on that? But what's BB transpose?
I.
Yep. So that's equal to A transpose. What's A times I?
A.
A. So that's A times A transpose. And what's A times A transpose?
I.
And that's it. So that's the proof in that direction. And the other direction basically is the same. Yeah, you also have to show that AB transpose times AP is I. And that just as easy. But isn't this pretty? Like, doesn't take any like brilliance. You just kind of write it out.
These proofs are much nicer today.
Aren't they sweet? Yeah. Okay. And again, I'm not going to prove all of it because I'm hoping that you know that if you switch the transposes, it'll still work. And inverse basically, inverse comes from the definition, because if you look at A transpose equals the identity and A transpose A equals the identity. Well, if it's inverse instead, you can switch them around and it still works. So same thing, same idea. Okay, so here's a question I have for you. We'll do something, just kind of imagine it. Let's suppose that you had a plane, okay? And let's suppose that you know two vectors on the plane. And you're given a third vector on the plane. Now, hopefully you know that the third vector can be written as a linear combination of the other two, right? Do y'all agree with that? That'll always work. Okay. But it turns out finding that linear combination is not that easy. And you can trust me on that. It's kind of a pain. Turns out that there's a nice way of finding a basis for vectors, and that is orthonormal. And what we want to do is want to say, well, how do we get orthonormal bases instead of just get any old bases? So if you're given a basis for vectors in a plane, so for example, if I tell you, let's say I tell you a plane contains the vector 2, 4, 5, and 1, 0, 1. Okay. And if I know the plane contains those, first thing, are those a basis for the subspace that the plane is? Is that a basis?
Yes.
Yeah. How do you know it's a basis?
It's the span of a set of vectors.
Yeah, but more importantly, how many vectors are there?
2.
And what's the dimension of a plane?
2.
2. So one thing we know it spans because we have the right number of vectors, or at least it might span, right? And they're not, if you look at these vectors, they're clearly not multiples of each other. They're not in the same direction. Can you see that?
Yeah.
Because the second one, first component is twice the first one's first component is twice the second one's first component, but certainly the second component is not twice the other second component. Okay, so it's definitely not in the same space. So the question is, we got a span of this plane. Now, do you think this is a very easy coordinate system to use for this plane? Think this is the best coordinate system? The answer is no. Okay, what you'd rather have two vectors that are orthogonal to each other, okay, and unit vectors. You'd rather have an orthonormal basis. So it's much nicer to be able to work with an orthonormal basis. Kind of like the standard basis in R2 is much nicer than any other basis. And that's because it's an orthonormal basis. So the question is, if I said, all right, I have a plane that's spanned by these two vectors, find an orthonormal basis. For this plane. Could you do that?
Probably.
Do you know how?
No.
No, you need help from two different people. Who are those people?
Graham and Schmidt.
Graham and Schmidt. Okay. And here's the Graham-Schmidt process. Okay. It's messy looking. And yeah, it's a bit messy. But the good news is when you have something that's step by step in the real world, why is it nice if you can write it as step by step?
Because then you can make your computer do it.
Exactly. But again, if you don't know how to code, then it's not going to help. So it means that you can code a computer to make it happen for you. Even if you're dealing with, a 30-dimensional space, you certainly wouldn't want to do Graham-Schmidt by hand. But a computer could do it in, less than a second. As long as you know how to program it, so you have to really understand the steps and how the process works. Okay, and a big part of, I don't know if you realize, but the reason why you need to take second year calculus for the hardcore STEM majors, the main reason?
I was thinking dealing with surfaces.
No. A little more abstract than that, a lot more abstract.
Jacobians?
Much more abstract. It's so you can do processes, is you can come up with strategies that are step by step and come up with solutions to problems that you have to deal with when you're an engineer or whether you're a physicist or whatever. And if you can come up with a step-by-step process and understand step-by-step processes and take a step-by-step process, adjust it slightly to what you need to do to make it work for you. So again, memorizing these processes is not what it's about. What it's really about is understanding how to make your own processes and how to learn processes. Does that make sense? That's what you need to do to be a very good engineer or a very good physicist or a very good whatever you're going to be doing in STEM, is to be able to come up with a step-by-step way of making it happen. And then you tell your team to go do it. You're going to have employees under you and you let them do it, but you have to give them instructions. Does that make sense? I'll let you know that's the main thing. So Graham-Schmidt is a good example of that, where it's a process. So here's how it goes. Let me read it out. Let's suppose that we have S, which is the set U1, U2, ... UK. And let's suppose that S is a linearly independent set of vectors. Okay. And by the way, for today, there are vectors in Rn, and we'll abstract that another day. Okay. So they're linearly independent, but they're not necessarily orthonormal. But here's the process to make them orthonormal, or to come up with a span or a basis for that same set that's an orthonormal basis. And it goes as follows. Step one is really easy. You just let V1 be U1. You just grab the first vector, because the idea is if you only have one vector, then orthogonal doesn't matter anymore because you can't dot anything. Is that clear? So just grab the first one. Step 2 now gets a little harder. We're going to let V2 be equal to U2 minus the quotient U2.V1 over the magnitude of V1 squared times U1. Okay, anyone lost on the symbols here on step 2? Anyone lost on that? Just a note, let's see if you can do this. What is V1 dotted with V2? If you dot step 1 and step 2, what do you get?
0.
Mm-hmm. Okay, you get 0 because it's U1 dot U2 for this first term. And you can take minus U2 dot V1. Okay, and then remember V1 is U1 in this case over V1 squared times U1 dotted with U1, but U1 dot U1 over V1 magnitude squared is just 1. So you just get U2 dot U1 minus U2 dot U1, and that's 0. Anyone lost on that dot product? Okay, so that's good. So that means we've gotten our second vector that's orthogonal to the first vector. Step 3 is you let V3 be U3 minus U3 dot V1 over V1 squared times U1. So basically it's the same thing that we just did. And then minus U3 dot V2 over V2 squared times U2. All right. So when we've reached step 3, we then have 3 orthogonal vectors. Step 4, continue till you're done. What does continue mean? What do I mean by that?
If you have a 4 component vector, do it one more time.
Yeah, you do it again. You're going to have a V4 is U4, and then you're going to have a dot product over the magnitude times U1, dot product over the magnitude times U2, and then you'll have minus a dot product over the magnitude times U3. And if there's another one, you just do it again. Does that make sense? So that'll give you your list of V1, V2, V3, all the way to Vn, or sorry, Vk. Now that will be orthogonal, but not orthonormal. But you all know, hopefully, how to get an orthonormal set out of an orthogonal set. And that is you just divide by the magnitudes. And that gives you your orthonormal set. And that's called the Gram-Schmidt process. Any questions on this idea? Okay. And this always works. So it's whenever you have a step-by-step, you don't have to write a proof because it's step-by-step. I guess you have to show the dot products are 0, but I kind of did that for the second step, and I'll let you look at it for the third step and realize everything cancels when you take a dot product. Any questions on that? I do want to mention something. Typically, if you can do it by hand, then what you're going to do is actually you're going to take V2 and you're going to do this mess, and then you're going to multiply by the common denominator, because then you have to do with fractions. And same thing with V3 and et cetera, et cetera. And the idea is then you don't have to worry about fractions. Any questions on that idea? Because if you multiply by a number, you don't change it being orthogonal. And then at the end, you make it orthonormal, and that's when you can do with fractions. A computer, you don't have to worry about it, because computers, unlike me, they don't complain about fractions. I hate having like a zillion fractions and have to do arithmetic. I don't know if you're like me, but probably you are. It's much easier not to have to deal with fractions. Any questions on this process? Okay, let's do this example. So let me copy and paste this one under it. Oops, that didn't work. Let's try again. There we go. All right. So what is V1? This is step one. Step one is easy. If you can't do step one, then you're totally lost.
V1 is U1.
Yeah, which is?
2, 4, and 5. 2, 4, 5.
Yeah. Yeah, that's supposed to be very easy. You just let V1 just be the first vector. Got it? Okay, now let's get the second one. The second one's messier. Not impossible, but it's messier. And let's get V2. And that one, it says I'm going to take U2. Okay, and U2 was 101. And then I'm going to subtract. I'm going to have a fraction. Let's make a fraction. And then I got to take the dot product, it says, of U2 and V1. Okay, so that's going to be 2, 4, 5. Dotted. I know there's a dot somewhere in here. There it is. Dotted with 101. And then I'm going to divide it by the magnitude of V1. So that, and the square of the magnitude. So that's going to be, how do you get the magnitude of V1?
It's the square root of 2 squared plus 4 squared plus 5 squared
Right, and we're squaring it, so you don't have to worry about the square root.
of 45.
So 2 squared, I think I'll write it out so you see what's going on, plus 4 squared. Oops. Plus 5 squared. And that's times U1. And U1 is 2, 4, 5. Any questions on getting this? All right, so now we got to deal with the mess. And that's going to be 101. Minus. And now let's do it. So we're going to have a fraction. What's 245.101?
7.
Yep, 7. And then 2 squared plus 4 squared plus 5 squared is 4 plus 16 is 20 plus 25 is 45, as you mentioned. And then times 245. Any questions on that? So now I'm doing this by hand. And as I mentioned, computers don't mind fractions. I do. I'm going to multiply by 45. I just need something orthogonal. So multiplying by a number doesn't change its orthogonality. Do you all agree? So I'm going to multiply by 45 to get 45, 0, 45. Minus, and that's 14, 28, 35. Any questions on that? Okay, now I just got to do this. Almost done. And 45 minus 14 is what, 31? 0 minus 28 is negative 28. And then 45 minus 35 is 10. And then I got to go 1 and 1 minus that, right? Let's see. Oh, no, I did that. Any questions on that? All right. It looks like I might have made a little arithmetic error. Can you find it? Because when I dot it, I don't get 0, and you're supposed to get 0 when you dot it. Anyone see the arithmetic error? This is why I like using a computer instead of doing it by hand, because computers don't make arithmetic errors. But somewhere in here, there's got to be an arithmetic error because, again, the dot product is supposed to be 0 when you're done, right? 25, 20. Anyone see it?
What do you dot it with to check?
If you dot V1 and V2, you should get 0. Oh, maybe that does give you 0. Let's see. Oh, you know what? I think it does. Let's see one more time. 62, and then 50 is 112. Oh yeah, no, it worked. Sorry. My mistake was doing the dot product in my head. Okay, so we now have V1, V2. Sorry about that. Is 2, 4, 5. Yeah, it did work. And 31, negative 28, 10. Is that an orthonormal basis?
No,
No. How come?
the magnitudes aren't equal to 1.
Right, we haven't done the last step yet. So now we just do the last step. So finally, we divide by the magnitudes. And I think I'm just going to do it the easy way, which means I'm just going to write down one over 2 squared plus 4 squared plus 5 squared. That was the 45, I believe, wasn't it?
Yeah.
And then this one's ugly. And when it's that ugly, I'm not going to do it. Instead, I'm going to write down 1 over. Oh, you know what I didn't do? It's not just one. It's not over 1 over 45. It's
the square root.
1 over the square root of 45. So I'm going to cheat and be lazy. 31 squared plus 28 squared. It's negative 28, but I don't care. I'm squaring it. Plus 100, which is 10 squared, but that one I can do in my head. And I'm going to assume that you know how to do arithmetic if you really needed to. And now we have an orthonormal basis. Any questions at all on this process? Okay. If we had, 4 vectors in 10-dimensional space or something, you could do the same thing. Then you definitely would want to use a computer program. But it's good to know the process, with 2 vectors and see how this works. Any questions at all on this example of Grand Schmidt? Okay, if there's no questions, Now let's talk about orthogonal projections. So here's a big definition. Let W be a subspace of Rn. Okay, so it might be a plane in R3, for example, something like that, that goes to the origin. And let's suppose we have an orthogonal basis, W1 through WK. And let's suppose Y is a point in Rn. Okay, that is not necessarily and not usually in W at all. So we might have a plane in R3 and then a point off that plane. Then the orthogonal projection of Y onto W. So you think about that plane, that point, and you're going to project the point onto the plane. Is Z equals the projection of W onto Y. And here's the formula. Y dot W1 over W1 squared, or the magnitude of W1 squared times W1 plus Y dot W2 over the magnitude of W2 squared times W2 plus dot 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 plus Y over Y dot WK over the magnitude of WK squared times WK. Any questions on the formula? Okay, so the orthogonal projection is the point in W that is closest to Y. Okay. I'm not going to prove that today, but how do you prove something like this?
Do it.
Okay, you're going to hate it because I'm going to say something that I have said before, but it's been so long ago that you probably all forgot it. Anyone know? Lagrange multipliers. Like I said, it hasn't happened since like May, I think, or maybe June. I think it was June that we did that in June in third quarter calculus. Does that ring a bell at all? So you can prove this using Lagrange multipliers. Am I going to do this? No. But this is the definition, and it is the closest. And that is because you can do some calculus and find the gradient and set the gradient equals lambda times the gradient of the plane, and then you'll find out that this is the solution. Sound good? Y'all trust me? And do y'all trust me you don't want to be seeing it right now? Okay, but it is important, and it's really, really important. Not the proof, but understanding, how to do this and what this is. This is the projection of Y onto W. Okay, the orthogonal projection. All right, so here comes an example. Let's suppose Y is a point 2, 3, 1. And let's suppose P is the plane X plus 2Y plus Z equals 0. And hopefully you can all in less than 2 seconds tell me that Y is not on this plane. Do you all believe that?
Yeah.
Yeah. There's no way you're going to plug in 2, 3, 1 and get 0 out of that. You can get some number that's positive. Okay. Find the point on the plane that's closest to Y. Okay. Now we did this in third quarter calculus, but now we have a better way. Okay. Before we use Lagrange multipliers, and now we can use the projection of P onto the plane. Okay. So what do we have to do? What's the first thing we have to do? To be able to use this big definition that we just had.
Let Z equal negative X minus 2Y.
You could do that. Not necessary, though. It doesn't hurt you, but I don't think it helps either.
Of Rn.
What's that?
Find a subspace.
Yeah, we need to find the subspace. Okay, which is not that hard. I like easy numbers. So how about 1 comma 0 comma negative 1? Do y'all agree that's on the plane?
Yeah.
Okay. So I'm trying to pick nice points. And then you pick another point that's not parallel. And to do that, how about, so let's not let y be 0 anymore. How about 1 comma, how about 1 comma negative 1 comma 1? You good with those two?
Yes.
Okay, now I got lucky. What happens when you dot those two?
Zero.
I get 0. Why is that good?
They are
They're orthogonal.
Yeah, now let's go back to this definition. We need an orthogonal basis. So I just found an orthogonal basis, luckily. If turned out if it wasn't orthogonal, what would I do then? Let's say I didn't get lucky. How would I get an orthogonal basis?
Grand-Schmidt process.
Yep, I'd use the Gram-Schmidt process, and that would work. So if you didn't choose these two vectors, you know how to do it. I wanted to spare you that pain because we already did one example, and I can only do so many examples of Gram-Schmidt. Okay, so that's so I got my orthogonal basis. So now what I want to do is I want to find and let me copy and paste so we have it, the projection of y on a w. And there's our formula. So now we just do it. So let's do it. So I'm going to just copy and paste again. And let's look at it. In this case, we have our y, which is 2, 3, 1. And just to let you know, this is kind of tricky, but or subtle, I think is the right word. There's 2, 3, 1 is a point. That's not a vector. Lowercase y is the vector 2, 3, 1. Do you agree that's subtle?
Yeah, so subtle I didn't notice it.
Yeah, it's hard. It's easy not to notice, but there's a capital and lowercase because capital is not a vector. You can't dot a point with something, but you can take that point and say, yeah, now I'm going to make those pointy brackets instead of nice, regular parentheses. And then I have a vector. So now I need to take, again, I'm just going to do this one at a time. I'm going to take y dotted with w1. So what is y dotted with w1? Here's w1, 1, 0, negative 1.
one.
1.
That's 1. Kind of nice, right? And what's the magnitude of w1 squared?
2.
2. And then w1 is 1, 0, negative 1. Okay. Then I do the same thing with w2. What's y dot w2?
Three.
What do you get?
I mean, 0.
I get 0. I tried to make a really easy example. Okay. And then I don't even care about the rest. Once you get 0, you're good. What about all this other plus dot 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 plus stuff?
Depending on how big our basis is, we continue.
No, but we have an example here.
That's 0 because there's no WK.
Yeah, it's gone. It doesn't even apply. Okay. In other examples, it could, but in this example, we're done. Do you see? Any questions on that? Okay, now we just do it. Again, I picked an example. I didn't know how much time I'd have. And I think I did it right. I wanted to pick an easy one. So what do we get?
One half 0, negative 1/2.
Yeah, I'm going to use decimals because it's easier to type. But if you want halves, that's okay too. So there's our projection. It turns out we don't even need the second vector, but that's not always true, by the way. You don't always get a 0 for a dot product. And that means that this point, 0.5, 0, negative 0.5, is the closest point on the plane to 2, 3, 1. And that wasn't very hard, was it? Hopefully you agree. And you could do this, you know, in many examples. Any questions on that example?
Do you know of an application and where this would be useful? Just off
Oh,
the top
yeah.
of your head?
A main one, which we're going to get to. So I promise. Well, like I said, it's probably the most important application of all of mathematics right now that people are doing for high money. So we'll get there. And I may not be able to convince you why what we're doing is what everyone else is doing, but it is. Okay. So let me give you this next definition. Let W be a subspace of Rn. Then the orthogonal complement of W, which we call W, the way you say this, by the way, is W perp. Nobody uses the whole word perpendicular, but for some reason, everyone calls it W perp, is a set of all vectors that are orthogonal to every vector in W. Okay, so just see if you can picture this in your head. If, let's say we're in R3, and let's say W is a line going through the origin. What do you think W perp is?
What was the question?
So we're in R3, and W is a line going through the origin. Right, that's a subspace. What do you think W's perp will be?
The XY
Visually.
plane?
It may not be the XY plane. It could be, but it doesn't have to be.
Vertical line.
Actually, it won't be a line, but good try.
The Z plane?
No, it'll be a plane
It
that's
will be
perpendicular to that line that also passes through the origin. Does that make sense? So it needs to be perpendicular. You might have been all picturing the z-axis, but I just said a line. I didn't say the z-axis. So if you just have a line going through the origin, then W perp will be the plane going through the origin that's perpendicular to that line. Any questions on that idea? Okay, so that's our definition. Okay, so here's a proposition. Let's see how we on time. Yeah, I think I want to get to the most important application. So I'm going to go to the proposition. W perp is a subspace. So again, W is a subspace. W perp is also a subspace. Okay. 2, the Rn perp, because Rn is a subspace of itself, Rn perp is equal to just the 0 vector. And then W perp perp, because remember that we now know that W perp is a subspace. So if we take the perp of that subspace, you actually get back at W. And visually that makes sense if you think about that line and plane, because again, if you have a line through the origin and its perp is the plane that's perpendicular to that line, then the perp of that plane is going to be the line that you started with. Do you believe that? And then finally, if you take your vector y, any old vector y, and you subtract the projection of y onto W, that'll always be an element of W perp. Any questions on this? And then finally, remember that the image of a matrix was a subspace. Do you remember that? So in particular, you can look at that image as a subspace and you can look at its perp and realize the proposition works for everything there. Any questions on this idea? All right, let's look at number one. I don't know if I'll prove all of these, but let's look at number one. How do you show W perp as a subspace?
By the definition of a subspace,
Yeah, how many things do we have to show?
3.
3. All right, so first, so let's proof of one. I don't think I'll be able to have time for all 3 of them, but I want to do one because one's really important. Well, what's the first one? Who remembers?
It contains the 0 vector.
Yeah. So what is the 0? Let's write it as a math symbol. What is 0 dotted with? There's my dot. Maybe that's a better dot. I had a better dot a while ago. I'll just use that dot. Dotted with some vector W in W. What do you know?
0.
0, that's good. Because as we want to show that 0 is orthogonal to every vector in W. Well, it is because 0 is orthogonal to everything. Do you agree?
Yeah.
So that was easy. 2 is easy also. What do we have to do for 2?
Show that it's closed under vector addition.
Good. So let's write it out. So let's say U dot all right, I'll use this bad dot. U dot W equals V dot W equals 0. So let's suppose that we have 2 vectors in W perp. Got it? For all W. Then, well, U plus V dotted with W. Well, we can use a nice rule of dot products, which is?
You can change the parenthesis.
Nah, you can't do actually. Starts with a D and not dot.
Distribute.
We can distribute. So U dot W plus V dot W. But U dot W is 0. And V dot W is 0. And what's 0 plus 0?
0.
0. So that one worked. Any questions on that? All right, now we can do the third one. Third one's easy. What did we have to do for the third one?
Show that it's also closed under scalar multiplication.
Yeah, so I'm going to do K times V dotted with W. Okay, but we had a vector property on this. What can we do? Now we can move the parentheses because you're allowed to. K times V dot W. But V dot W is 0, so that's K times 0. And that's equal to 0. Any questions on that?
My only question is why are we dotting each thing with W?
Oh, because we're checking to see if it's in the orthogonal complement. Definition of orthogonal complement means that it's orthogonal to every vector in W. So I'm going to take a vector in W, I'm going to dot it, and
if
needs
it's
to be 0.
orthogonal, it'll be
Yeah.
0. Got it.
Yeah. So that's the name. That's the word orthogonal. It means dot and you get 0. So I dotted and I got 0. Okay. I don't think I'm going to prove the rest, but it's not that hard to do. Number 2 should be obvious, that 0 is orthogonal to every vector. Do y'all agree with that?
Yeah.
And 0 is the only vector that's orthogonal to every vector in Rn with n big, at least as big as 1. Do you agree with that too?
Yeah.
Yeah, there's just there aren't any others that is orthogonal to everything. Okay, so that's kind of obvious. Number 3 is that the orthogonal complement of the orthogonal complement is what you started with. That's actually really easy to prove. Okay, and that is that if, say, U is in the orthogonal complement of W, complement, let's make this a, oh, I know, this way. We want to show U is in W, right? Well, then U dot W perp is equal to 0. Then for every, how about V in W perp, U dot V equals 0. Any questions on that? But the thing is, now we know what vectors are orthogonal to everything in W perp. Well, they're the vectors in W, right? So therefore, U is in W. Any questions on that? Okay, so that's the big theorem. Okay, now comes a lemma. Very helpful lemma. This you have to think about a minute. If we have a matrix A, we multiply by a vector X, and then we dot it with a vector Y, then that is equal to X dot a, oh, that shouldn't be perp, that should be A transpose. A transpose Y. Why is that true? So why is it true that AXY equals X A transpose Y? Anyone see why? Don't see you jumping in.
Because you're dotting or multiplying with respect to X in the first one, and then on the other side, you're dotting with respect to Y, so you change rows and columns.
Yeah, so it has to, right, it has to do with the dot product. The dot product is actually, is really a matrix multiplication, right? Matrix multiplication is a dot product, right? And what AX does, you take X as a column vector, and then you dot it with A in rows. Does that make sense? But dot products can go backwards. Remember that say dot B equals B dot A. Has to do with that. I think I'm not going to give you all the details because I want to give you the big, huge example. Application, I mean. But do y'all believe this is true?
Yeah.
Okay, so now comes least squares. And this is, again, probably the most important application of the whole class in terms of useful. So let's consider AX equals Y such that there is no solution. Okay. Now, have we seen these kind of equations where you get no solution?
Yeah.
Yeah, happen a lot, right? You join the matrix and then you RREF. And if you get if the bottom row is all zeros except for the last one that's not zero, then you say no solution, right? And what do you do after you say no solution? What have we done in the past?
Made a linear combination of the ones that were solutions.
No, that's not what you did. You moved on. Said, I'm done. Isn't that what you did? You said there's no solution. Let's go on to the next problem. You don't remember doing that? Yeah, if there wasn't a solution, then you just quit. But it turns out that's not what we want to do. Okay, what we want to do is we want to find not the solution, because there may not be a solution, and there's often not a solution. We want to find not the solution, but of all different vectors, which one's closest to Y when you do AX? Any questions on that idea? And what you do is you take AX equals Y and you multiply you left multiply by A transpose. And this is where you trust me that this is a good idea. Do you believe you're allowed to do that? Okay, so we can write down A transpose AX equals A transpose Y. Do y'all believe that that's equivalent to AX equals Y? Okay, why is that helpful? Anyone know why that's helpful?
We can find Y.
We're actually not looking for Y. We're given Y. We're looking for X. Okay, the reason is A is not necessarily and not usually a square matrix. Okay, and if it's not a square matrix, it's much harder to do anything. On the other hand, A transpose A is always a square matrix. Do you believe that?
Yeah.
Well, if you have a square matrix, you have at least a possibility that you have an inverse. Do you believe that? Whereas if you don't have a square matrix, you can't, forget inverses. That's not going to work. When you have AX equals Y, you can't just say X equals A inverse Y, because A inverse may not exist. Is that clear? But if you have a square matrix times X equals something, then you could take the inverse of both sides. Okay, now it turns out that if A is general, so if you randomize numbers in a square matrix, okay, so if you randomly select and literally statistically randomly select numbers and put them in a matrix, what do you think the probability of it being invertible is?
No idea.
Okay, this is going to be a surprise. 100%. 1. Okay, because if you remember in TFAE, we know that a matrix is invertible if and only if the determinant is non-zero, right? Okay, the determinant comes from these random numbers. Well, if you randomly pick a number, let's say from negative 100 to 100, what's the probability you're going to pick 0? if you're including, you know, every possible decimal. You're not going to, right? Do you agree?
Yeah.
So it turns out that for random variables, and in particular variables with noise, because that puts some randomness in it, A transpose A will always be invertible. Got it? So now we can actually solve. And we can say that X is equal to A transpose A inverse times A transpose Y. Any questions on that?
That's quite fascinating, honestly.
Yeah, but it's even more fascinating when you realize what the point of all this is. It's kind of cool mathematically. But now let me give you the big example. This is gigantic. Okay. Gigantic means it's really used. Not with these numbers. I just grabbed some numbers. And I'm not gonna actually do the full calculation, but I'm gonna show you how it works. Okay, so let's consider the points 0, 4, 2, 3, 3, 0, 4, 2, and 5, 5. Okay. Now, do these lie in a parabola?
No.
No, they don't. Okay. And you could test it and see, and you'll realize that they don't. Okay, they don't lie in a parabola. So what we want to do is we say, well, they don't lie in a parabola, but what's the best fitting parabola for these points? Does that make sense? So how do we do that? And we've kind of already talked about finding a parabola. Do you remember how you found a parabola before? What did we start with? It's very simple.
Plotting points.
Yeah.
Um,
The zeros, right?
no, we didn't plot points.
Right. Are you talking about like in
You wrote
pre-calc
down
or in this class?
in this class. Yeah, we actually talked about finding the parabola when there were only just 3 points. Now we got 5, which means there's going to be a parabola.
We wrote the general form equation for a parabola.
Exactly. So let's do that. AX squared plus BX plus C. Okay? Equals Y. Okay, or Y equals however you want to write it. Any questions on that? Then what we did is we just plugged them in. So if X is 0, you're supposed to get 4, right? So that would mean C equals 4. Now be careful, because C actually doesn't equal 4. I know that sounds really dumb, but I'm just letting you know for now. And then if X is 2, you're supposed to get 3. So if X is 2, we get 4A plus 2B plus C is equal to 3. Got it? Okay. And then if X is 3, you're supposed to get 0. That's 9A plus 3B plus C. In fact, I think I can do this a little differently. I'm going to write it the way it's really written, because no one does it this way, even though it's the way you want to do it. I'm going to write A plus BX plus CX squared. Trust me. So we say A equals 4, and then we're going to have a 0, 2, 3. So that's going to be A plus 2B plus 4C equals 3. And then for the third one, we have 3, 0. So that's going to be A plus 3B plus 9C is equal to 0. Next one is 4, 2. A plus 4B plus 16, C is equal to 2. And the last one is 5 comma 5. So we get A plus 5B plus 25C is equal to 5. By the way, any guess on why I switched these around, made it look like what you're not used to, A plus BX plus CX squared?
So you could have a row of ones or a column of ones.
Now you'd have that anyway. You'd have the last column be ones. That's not the reason. There's a reason. Should I tell you? So that you can generalize this to nth power and write this as a power series. Okay, as a Taylor polynomial, actually. And you want the best fitting polynomial of nth degree. Can you imagine doing with 5th degree? And you could do 100th degree if you really wanted. All right, well, now that we have this, we can find A. Wonder if I can do this. Yeah. Okay, so now we can do our equation. And the equation, the matrix equation, we can turn this into a matrix equation. So what by what matrix is this going to be?
5 by 5?
Not 5 by 5. It's 5 by 3. Because it's 3 variables. And we're going to have 4, 0, 0. I'm sorry, not 4, 0, 0, 1, 0, 0. Then we'll have 1, 2, 4. Then 1, 3, 9. Then we'll have 1, 4, 16. And then 1, 5, 25. And that's our A, capital A. Any questions on that? Okay, and notice, by the way, our Y is going to be 43025. Any questions on that? And then it's really easy by computer. Let me just remind you, I'm not actually going to do it because we don't have any time, but all you do is you take A transpose times A inverse times A transpose times this Y vector, and that'll give you your X. And the X will give you your A, B, and C. So that'll tell you what the best fitting parabola is. Do you believe that this is not that hard in a computer to do? You know, Desmos, I mean, not Desmos.
Nah, Excel does it all the time.
What's that?
Excel does it all the time.
Yeah, Excel does it. I like Symbolab, but if you like Excel, that's fine. But I mean, to understand the linear algebra, you do it with the Symbolab. Can you imagine doing this with a cubic instead of a quadratic?
No.
Why not? You could do it. You just have a 5 by 4 matrix. Do you see? You could do it with, say, a logarithmic equation or exponential. Same idea. As long as they're coefficients. Does that make sense? So let me tell you the hard part in terms of real world. Anyone guess what the hard part in the real world? So let's suppose you have, 1,000,000 points and you want to find out what the pattern was for those points. What do you think you'd do using this kind of information? Okay, and the idea is, let's suppose you picked a best fitting polynomial. What degree of polynomial should you pick?
Probably pretty high if you have 1,000,000 points.
Okay, not necessarily. And this is hard. And I can't explain how to do it, but there's some serious computer programming going on to come up with the best degree to use. Because once you have the degree, it's very easy because we have a formula, right? An equation. Very easy to program a computer to do it. Coming up with the best degree is actually very difficult. And you need some sophisticated AI to do that. But the money's good. Any questions on that idea? Because if you have too high a degree, you actually what's called overfit the data. So if the data really was kind of like a line and you did a 5th degree polynomial, it's going to be all over the place when it really looks like a line. And 5th degree may not have been the right thing to do. All right, we're out of time. So let me stop my share. And let me stop the recording. We'll come back Monday.